Right, thank you. Thank you very much for that brilliant introduction. Right, I hope I'll do justice to it. So what I want to do is, over the next 40 minutes or so, just take you briefly over some of the reasons why X-ray FELs, at least I think, and many others I imagine as well, are quite as interesting as they are to advance various areas of science. So I'll tell you a little bit about the things that I do, which is mainly based in the realm of this thing called high energy density physics. So I'm interested in very dense, very highly energetic systems related to plasma physics investigations. But I'll also talk about some slightly more biological type things, which have actually very, very close links with plasma physics, perhaps links that are not immediately apparent. So what I'll do is I'll briefly take you through some basic concepts. Some of these might be familiar with most of you, some might not, simply to motivate the rest of the talk. So I'll tell you a little bit about, well, why free electron lasers and so on, and what is the main advantage of using these things compared with other sources, and why they're quite as interesting as they are to advance some quite specific and varied parts of physics investigations today. I'll talk a little bit about some of the recent work on coherent diffraction imaging on FEL, simply to illustrate one of the more promising aspects of free electron lasers in trying to unravel the structure of various kinds of systems. But also then, because it leads on to the sort of things that I'm a bit more interested in, that's the fundamental X-ray matter interactions at high intensities. And what we'll see is that a lot of the limitations, or potential limitations in the future of CDI and so on, are related to the way we understand how very, very hot energetic electrons interact with systems on very short timescales. So anyway, the main idea behind this is, well, so there are two reasons why you might think you want FELs. So this is a reasonably busy slide, but the things that I want to draw your attention to is, the first thing is that if you want to look at molecules and atoms and relatively small things, as we do, then you'll need wavelengths on the order of somewhere between an angstrom and a nanometer. So you need that to do that sort of physics. So if you're interested in looking at these small things, and that's what we're going to be doing here, then X-rays are pretty much essential. Now, a lot of the diagnostics that you use, of course, for these require X-rays, but you need a lot of them, because a lot of the interesting techniques that you want to deploy to study these systems are so-called photon hungry, right? And so the more X-rays you have, the better. And it turns out FELs can deliver on that. Another thing that's very interesting is if you want to go and look at dynamics, right? So structure is very interesting, tell us where things are and how they relate and so on. But the dynamics is really where all the interesting things in physics happens, and in chemistry, and in biology, and so on. And it turns out that the way you study dynamics is you have to look at things on the time scale at which they evolve. And it turns out there are a lot of processes that happen on time scales that are sub-nanosecond, or sub-100 picoseconds, or so on. And it turns out that a lot of the X-ray sources available before the advent of FELs that are bright, sufficiently bright to use a lot of the fascinating techniques that you can use, so spectroscopy or scattering or so on, are pretty much confined on things like synchrotrons to about 20 to 40 picoseconds, right? And so if you want to look at things that are on shorter timescales, you either have to come up with a camera that's much faster than that, and that's hard to do, or come up with a machine that can deliver very, very short pulses, and you take instantaneous snapshots. And that's the theme behind a lot of things that I'll be talking about later on, right? This idea that you can take X-ray snapshots in time, and that then tells you something about how the system is, and you try and freeze it in time. That's the idea behind this. And then you freeze it in time in a sequence, and then that tells you how things evolve. So these two, the merging of these two things is probably why X-ray FELs have turned out to be so useful, and that is because they do merge very, very short pulses. And now I think typical pulses you can get down to below a femtosecond with very, very high energy. Okay, so as I said, this is the region that we want to be looking at. Now, when you have a set of X-rays and they interact with a single system, so an atom or something, there are typically three types of things that can happen, although there are various ways in which each of these can happen, right? One is absorption. So you absorb a photon and you excite or you ionize or you do something to the electrons. Typically, they fly out. You give them more energy. And so this happens quite a lot, of course. There's scattering, inelastic, elastic, all kinds, doesn't really matter. The point here is you get a photon in, you get a photon out. You may or may not excite the atom doing so. Again, it doesn't really matter. And then, of course, you have pair production. This is the sort of thing that we're not going to talk about because we'll never get into this regime now. So it's really a competition between absorption and scattering, right? So when you shine X-rays on matter, that's really all that can happen. This here is a cross-section diagram that shows you the various cross-sections for these processes for carbon. So I'll talk a little bit more about this in some of the following slides. But the important thing to note is that if you're looking at the ratio between the cross-section for coherent scattering, which is the solid red line, and photoabsorption, then you'll see that by and large it's very difficult to beat scattering, right? So you'll find that it's easier to absorb than it is to scatter. And that for some things is a little bit of a problem. Okay, so when you have a single atom, of course, that's all that can happen. There's a very interesting thing that happens when you have an array of atoms, right? So when you have a lattice. So this is, again, a fairly simple slide, right? But the idea is that if you have a whole bunch of atoms stacked in a periodic system, so you get a crystal or something like this, then you can get a very nice type of scattering, which is also known as Bragg diffraction. And this is the basis of most of crystallography in biochemistry and in biology and so on. It's the way most people understand how most things are made of. So it's a very, very interesting process. From the point of view of X-ray matter interactions, it's great, because what happens is your X-rays are scattered, of course, but they're now scattered off planes. And because you have a periodic structure, the K-space representation of the scatter beam is also going to be some sort of, it's going to have a lattice, right? And so what you'll get is you'll get these things called Bragg peaks on your screen, right? So you run your X-ray beam through some sample, you get Bragg diffraction off it, and you get some very, very bright speckles. You get these dots, these Bragg peaks. And the nice thing about that is that that has a nice relation to the crystal structure that you're looking at. So you can use an image here, so this is just done of salt, to invert that and to determine what the structure was like. Right? So this is a very simple idea, but it's on the basis of almost all the non-spectroscopy experiments that are done on X-ray facilities. It's immensely powerful. But it relies on the fact that you have a crystal, right? So, okay, so how do we make a bright X-ray source? So the first type of sources, the most common ones maybe, are just an X-ray tube, right? So here you use little electrons and they come in and they create a Bremsstrahlung background. And that's nice. It gives you a lot of nice X-rays, right? But it's not quite enough to do the sort of things that I'm talking about. So the next best thing you can do is, of course, synchrotrons. And these are wonderful facilities. They've been around now for many years. And they are the workhorse of modern biochemistry and biology and structural biology in particular. And basically, the sort of interactions that people look at here are Bragg diffraction, right? That's the sort of thing that you'll look at. And then you'll do imaging of that. So the way this works is, of course, you have an electron beam. It circles around. And then you send it through undulators. That produces X-rays. And these X-rays are bright, very, very bright, far brighter than this, right? And they allow you to do some very interesting science. So up until about, well, 10 years ago now, this was the best way to create a bright X-ray source. That's the best you could do. And it had several limitations. The most important of them was that the energy and the pulse length were limited to what you could do with a typical pulse. Now, the difference between an FEL and a synchrotron is fundamentally not that huge, right? But the idea is that when you have your electron beam, and of course, even in a synchrotron, in most third-generation synchrotrons, the electron beams will fly through an undulator. The nice thing here is, of course, that if you make these undulators long enough and you tailor the beam in just the right way, then you can have a feedback loop between the photon field and the electron bunch that is flying through, and you create this thing called microbunching, which is shown here. So you have your bunch, and it splits up so that it's now aligned with the wavelength of the radiation that's going out. And so what that allows you to do is that whereas before you had an incoherent source, right, where all the various peaks and troughs of the field would effectively interfere destructively most of the cases, you can now have constructive interference between these. And so you can generate much, much, much larger fields because you bunch your electrons. So, and what this allows you to do is create a very, very, very bright source. So that's effectively the only real difference. Of course, it's actually quite hard to do, right? But on a conceptual level, there's not a huge amount to it. Now, the nice thing about this is whereas this scales as n, this now scales as n squared, and so you have a saturation process, and you create something that is much, much, much brighter indeed. Okay, so how long an undulator do you need? Well, so these are the undulators at LCLS, which is the Linac Coherent Light Source at SLAC, and it's about 130 meters of them, right? So you need quite a long distance of things. You actually don't need the full 130 meters, right? But you need quite a lot of them to get this effect to work. But it turns out that it works, which is great. So this here is a nice picture of the facility from the sky. So for those of you who are familiar with SLAC, this here is the SLAC Linac, a nice and very famous workhorse for particle physicists, which then retired it because now the useful particle physics is probably happening in CERN, the sort of things they used to do here. and it was converted into a light source. So you only use about a third of the Linac for the beams. Maybe this is a slightly better picture from above. So you use about a third of the Linac. You use that to create a very energetic electron beam. Then it goes, this is all underground, of course. It goes through a tunnel. Your undulators sit here. And then it goes again underground under this building, which is the so-called near experimental hall. And you have a whole bunch of hutches. And then you have another bunch of hutches underground under this hill over here, right? So you're talking about a facility that's, well, relatively large, right? These are large-scale facilities to do this. So this is what the undulator hall looks like. It's very big. And then you have some type of experimental end stations. So this is the first X-ray free electron laser that was operational, and it saw first light in 2009, right? So it's been around for just under 10 years now. It's been delivering some spectacular science. After it came SACLA about 2 years later. So this is a similar facility in Japan. It's slightly smaller. It can do a lot of similar things, but not quite. So this is a storage ring, and that's the FEL. Again, relatively large facility. And this here's a facility that's currently being commissioned in Germany. So this is called the European XFEL. It saw first light, I think, 2 years ago now, possibly. But it started operation, and we were involved in the first experiments, I think, at the end of last year. And so these are all things that are fairly new, and they're coming up. So this facility is large. This is the end station. Most of the facilities are underground. This is what it actually looks like on Google Maps. This is about 3 kilometers across. That's half a kilometer right there. So it starts here. That's your injector. That's your superconducting Linac that accelerates your electrons, and then you have your various beamlines and so on. It's so big, in fact, that it goes out of the state of Hamburg. So the state of Hamburg, which is where it's built, that's the border. So the beam starts in Hamburg and then ends up in Schleswig-Holstein, as a matter of fact. So these are very, very large facilities, because to get to the electron beam energy that you need, you actually need a very, very long accelerator, right? But it delivers something quite spectacular. So I used the term brightness a few times, right? So you might wonder what actually distinguishes a certain X-ray source from another one, and the answer is spectral brightness. So I'll talk about peak spectral brightness, and that's what I really mean when I say brightness. But what it is, and it's very important to distinguish it from intensities, right? A lot of times we talk about intensity as the thing that tells you something, but intensity is not a good number because it depends on the optics that you use, right? So what is brightness? Well, it's effectively the radiated power per unit everything, pretty much. That's what you want, right? So for unit area of the source, solid angle, and so on. The spectral brightness also divides it by the bandwidth. So it's the amount of photons affected, the power of the photons that you have within a specific bandwidth. And then the peak spectral brightness is, of course, for a pulsed source, you only divide by the pulse length, right? So you could have a CW source, a continuous wave source, where the average and the peak brightnesses would be the same, of course, but these are all pulsed systems, right? So the electron bunches come in pulsed streams, and so you get an array of pulses at the LCLS at 120 hertz, at the European XFEL at about a megahertz, right? So the peak spectral brightness is the quantity that we care about, this BW over here. And it's that thing that is conserved in passive lossless optical systems, right? So if you want to compare two sources, that's the quantity that you've got to use, because it's the quantity that effectively tells you whether or not your diagnostic is going to work, right? Whether or not it's possible to do what you want. Okay, so how does it compare? Well, there's an enhancement of about 10 orders of magnitude in peak spectral brightness between an X-ray FEL source and the latest third-generation synchrotron, right? So this is where all the interest comes from, right? So these are, of course, amazing machines. Your brightness is here of 10 to 24. When you go up to the peak, the average isn't actually that much different, because these have much higher repetition rates. But the peak brightness that you can achieve is over a billion times larger. And that is now significant, because it now enters a new regime of things that you can do with this that you simply couldn't do before, because you didn't have the right amount of brightness. The real only downside is that they're quite expensive, right? So you can't quite have as many of them as you like. Okay. Now, to try and get a feel for exactly what this means, right? Because, okay, I can say the peak brightness is 10 to the 32 photons per blah, 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 right? That's a number that's maybe not that useful, right? One thing you can think about is you can try and compare it to thermal X-ray emission, just for the fun of it, right? So you could say, okay, well, so thermal X-ray emission, say you wanted to get emission at 1 kilo electron volt from a thermal source. You can ask yourself, how hot does that source have to be to give you a black body spectrum, right, of that sort? So you can go through that, and you'll find out that actually it has to be quite hot, right? So to get a black body emission that peaks around 1 kilovolt, you need to go to sort of the temperatures in the core of the sun. So that's quite hard to do, right? But you can go further and you can ask yourself, well, how does this compare with the brightest X-ray sources that we know, right? Again, we're looking at brightness, which is normalized per the source size, of course, not total amount of energy. Some of the brightest X-ray sources we know of are active galactic nuclei, right? And this here is a paper that I dug out from, well, this paper here, where they estimate that intrinsic brightness temperature of this system is between 1 and 10 million eV. So these are electron volts, right? These are not Kelvin. So we're talking about 100 billion degrees. This is a ridiculous number, of course, right? Super, super bright. But you can then plot that on this curve over here, right? So you can plot the brightness temperatures of these things and compare them with these free electron lasers. And of course, there's a huge gap between that, right? So you have a system that, at least in terms of brightness, obviously not in terms of energy or anything like that, right? But in terms of brightness, they're some of the brightest sources that you can imagine. And that has some very interesting consequences, because now, for the first time, you have enough oomph in your beam to actually create dense plasma systems. So that's one of the things that I'm particularly interested in, because you now, with a single X-ray pulse, this is now bright enough so that if you focus it onto a target, you will create a very, very hot, dense plasma system. And that's exciting, because if we can create it with X-rays in a very nice, tailored way, and we can use that to try and study some of the extreme states of matter that we're interested in for an array of reasons. So when I talk about extreme states of matter, so these are just a little bit of terminology in high energy density physics. I'll go through this very, very quickly. But there are two sort of things that we care about, and they're under these not that useful names of warm and hot dense matter. But the idea is that these are systems that are dense and relatively hot. So this is temperature in EV, right? 1 electron volt temperature is around 10,000 degrees, just to give you a feel, 11,000, right? But the idea here is that they're warm in the sense that they have a lot of thermal energy, but they're also dense in the sense that you typically also have a lot of potential energy in them, right? So the density is quite high, and because of this, so this is this gamma equals 1, this plasma parameter, close to 1, you have some very interesting physics that is very difficult from the computational point of view, right? So it's quite difficult to understand. Now, these systems are of broad interest for various applications. But the sort of things that we're looking at is, so this is a phase diagram for hydrogen, temperatures between 1 to 100, 1,000 electron volts now, of course. So we're talking about tens of millions of degrees. And densities, well, you can start off around solid density. You can compress or not, right? But we're talking about a roughly solid density and things heated by a factor of, 1,000, 10,000 or so. So these things tend to be very, very widely found around in nature. I mean, they're present in all types of laser plasma interactions, and there's a lot of interest in that. But if you're interested in planetary physics and so on, the cores of planets, our planet included, lies on that diagram quite high up, right? The densities are quite high, the temperatures are quite high, but they're not, the temperatures aren't high enough to make this just a relatively classical plasma, right? This is effectively a condensed matter system that also happens to be hot enough so that all your nice perturbative expansions of things that you like to do in condensed matter physics doesn't really work, right? And so it's quite difficult to do. And that's part of the reason why experiments are so useful in this. Exoplanets is another reason why people care about this, because trying to understand the equation of state of these systems is important to try and understand the decomposition of these. So I downloaded this, I think yesterday or the day before. So there are about 3,000 of these confirmed planets. It's a beautiful website. You can go through it and click through all of them. But so, yeah, so anyway, going and growing, right? And so a lot of the physics of how these materials behave and what they're made of is going to depend on what your understanding is of how systems react under compression, under high temperatures, and so on. Right, so that's the warm dense side. What's the hot dense side? Well, it's just hotter than the warm, effectively, right? So, okay, that's predictable, right? But typically what you should be thinking about is inertial confinement fusion, stellar interiors, things like that, right? And so if you just look at, so this is a capsule from the National Ignition Facility, right? So this is a big, large-scale program to achieve fusion burn in the US, right? And of course, this capsule, between the beginning and the end of its irradiation and its sort of lifetime, goes through that entire phase diagram, right? So it starts off as something cold, it goes to the warm dense matter stage, various bits of it then go into the hot dense matter stage, and then way beyond, hopefully sometime to fusion burn, right? And so, of course, understanding these sort of processes require a lot of understanding of extreme states of matter that we're interested in. But there's also a lot of solar physics that you can do and solar opacities and so on. Okay. So the thing that's interesting here is that you could ask yourself the question of whether or not you now have enough energy in this pulse to try and create these systems. And if yes, can you do it in a tailored way, right? And it turns out that, of course, not all of them, but there are some systems that you can create in this, and you can heat your systems on a very, very short time scale simply by X-ray radiation, right? And the way X-rays typically interact, as I said, is just absorption or scattering. But that's fundamentally easy if you compare it with how optical light interacts with things, right? Because X-rays are just photons. So it's just particles flying around. So you can do something with that. Laser light, how laser light interacts with solids, that's a lot harder, right? And so we try to keep things, we try and work on the simple things that we might be able to understand. And this is probably the simplest you can get in terms of trying to create extreme states of matter. Okay. So I'll now take you through just a few experiments just to give you a feel for what you can do with these sources. Now if I've hyped them up, right? And the first is going beyond crystallography, right? So crystallography, some of you know this, some of you may not, right? But the whole idea behind crystallography is you're interested in some protein, you want to know what it looks like, right? What it does. Typically it's in some person or in some animal or in something, some drug, and you're interested in how it interacts, or you want to know if it's useful, right? And then what you do is you take it out of that place where it's actually useful and you make a big crystal out of it, and you hope that doesn't do anything. And then you stick it on a synchrotron, and then you shine a whole bunch of X-rays on it, and you make sure the dose isn't high enough to damage the thing. You collect a pattern, and then you use that pattern to invert back and recover what the structure was in the crystal, and then you hope that that tells you something about what the protein looks like, right? So it's fairly straightforward, but there are a few issues with this, which sometimes matter and sometimes don't, right? So first of all, it could be very time-consuming or hard to make large crystals, right? The larger the crystal and the more X-rays you can put on, the better the signal, so it's a good idea to do that. Some proteins you just can't crystallize, so you're stuck, right? Some proteins are just hard to crystallize in large enough crystals to get a good enough signal within a human lifetime on one of these things. So that's, again, another problem, right? And small crystals, while much easier to make, don't give you enough signal. So that's tough. It's also true, and this is kind of obvious, right? But crystals aren't the natural environment for these things. So ideally, you'd want to do this imaging in situ, or at least you'd want them in a solution or something like that. But that's completely beyond the capabilities of any of these machines. You just don't have enough photons. By the way, that's beyond the current capability of Xray free-electron lasers as well, right? But there's hope. And the problem, of course, is the non-periodic systems are hard to see in the X-ray scattering sense, right? Because you rely on Bragg's law. You rely on the fact that you have constructive interference between multiple instances of the same thing, and you see good stuff. If you take that away, what you're left with is effectively diffuse scattering. That's tricky, right? And so most of the things that people do, certainly on the level of proteins and so on, relies on the fact that you do have crystals in some way. And to some degree, that's still true today. Okay. Now, there's an issue of X-ray dose, which is very, very important on these machines because, of course, so X-ray dose is just the amount of damage that you induce in your system, right? So the question there is, when my X-rays interact, there'll be scattering, which gives rise to your diffraction, but there's also going to be absorption. And if there's a lot of absorption, right, too much of it, so the sample heats up, you could damage your system. And then you'll be imaging a damaged system, not the one you should have originally, right? So you have to use larger samples, or you can do some cryocooling and so on. And so this is, of course, done and very useful and great, but it's not ideal. In an ideal world, you do something different. Okay. So this here is an idea that came up to the group of Janos Heido in Sweden back in 2000. This was one of the reasons why people really pushed for FELs. And this is this nice idea of so-called diffraction before destruction, right? So the idea is the following. Okay, so on synchrotrons, we take so much care not to damage the system, and then we leave it there, and we irradiate the same system for a long time. Let's just not do that, and let's just give it everything we got, and let's blow it up to pieces, but let's hope that before it blows up, we can collect all the signal we need, right? So the idea is you deliver a huge amount of dose, right? So that's your dose there. I'll tell you in a minute what that is in gray for those of you who know a little bit about medical physics. It's a ridiculous number, right? So you're going to completely obliterate the protein. It's going to fly in all places. It'll be completely killed instantaneously almost. Well, instantaneously, in 50 femtoseconds here, right? But if you can collect enough signal early enough, that will still tell you something about the system, right? Brilliant idea. Does it work? Well, the first experiment for this was done several years later, right? So the assumption on this is that somehow you can beat photoabsorption, right? So you see that for most wavelengths, so this is an angstrom, that's 12 keV, all of the stuff that I'll be talking about is done in this window here. So this is for carbon, of course. For other elements, it'll be different, but carbon's one of the important ones. Absorption beats coherent scattering, and there's no real way to get around that. So you could worry about this, and you should worry about it, but it turns out it still works. So this is the first experiment. This is done by Henry Chapman back in 2006, is the little cowboy. So this is an etching on a silicon nitride frame, which is stuck here. And this was done on the flash soft, well, UV really, free electron laser, the precursor to the hard X-ray machines we have today. And you take a diffraction pattern. That's what happens when you do the first pulse. That's the second pulse. So this is the actual diffraction pattern of this thing, and that's the diffraction pattern of a hole. So the first pulse obliterates the sample completely, and you just have a hole, so you get nothing after that. But you can take the diffraction image here, and you can recover what the system looks like. Right? So this was proof that you could actually recover something by blowing it up. It's the first experiment that did this. And it's quite a neat experiment. Right? So this is the original plate, and this is the reconstructed plate, and that's the hole, if you want to see it after the damage. Right? So this is a proof of concept that you could do this, right, in the soft X-ray regime. But of course, this was done, I think, at 30 nanometers, right, which is not quite the resolution you need for protein. You need a little bit more. So I'll tell you about one case, although there are now several very, very fascinating experiments on this. And this goes over trying to understand photosynthesis, which has been one of the interesting types of systems that people have looked at, partially because it's a membrane protein, so it's hard to crystallize. You can't really do much with it. And it's one of the first things that people have worked towards getting a crystal structure out of it from an FEL. So this is work that was done on the LCLS. And so we're going to be looking at the various types of photosystems. But the idea is a photon comes in, trickles down, and then you have some electron capture. You split the water, and then the electron travels around, eventually creates energy. And so this gives you both a way to make glucose, which is useful, and a way to make oxygen, which is also useful, right? So ideally, you'd want to, so this is a cartoon, right? Ideally, you want to see this using X-ray diffractive imaging. So this is sort of the experiment, again done by Chapman. Now this is only 8 years ago. You have a liquid jet with your samples going through. That's your diffraction pattern. For large angles, these are small angles, right? And you use that to reconstruct. So this is what the diffraction pattern looks like. And these are some of the diffraction of the little nanocrystallites that you see. So of course, and what you can see is that between the Bragg peaks that you have here, you have a whole bunch of little fringes, right? So if you count these fringes, what these fringes tell you is how many unit cells you have in a single nanocrystal, right? So you get, of course, the scattering, the diffraction pattern of the actual nanocrystal structure, right, which is reconstructed here. But then within this, right, you also then get information on the actual system. So this is now the reconstructed system, right? So this is some of the indexing. I'm not going to spend too much time on this, right? But you can reconstruct the three-dimensional sample. And you can do this with sufficient accuracy, right? So this was done in 2011 for the first time. Okay, so now we have a simple snapshot, right? But what we really want to do is you want to see how these things interact with light or with something else. And so we want to see dynamics, right? So how do we do that? Well, it's a very old idea, and I think this is a very nice story, and it's fitting to talk about it while talking about another facility at Stanford, because it addresses the very same problem, but in a way that is maybe only too familiar to us today, right? And that's, well, how do you figure out something that happens too quickly for you to see? You try and slow it down, right? So this was the idea of photography. So there's this question that Leland Stanford asked himself, right? If the horse, while trotting, ever lifts all of its feet off the ground, right? Or if it's always in contact at some point, right? So this was called unsupported transit, right? A very scientific name for this. But the problem is that if you just look at a horse trot, it's hard to see because it's trotting quickly, right? So some people said, oh yes, some people said no, right? You didn't quite know. And the guy who solved it was this very, very weird Englishman who ended up killing someone for sleeping with his wife and was then acquitted because that was considered an acceptable thing to do back 100 years ago. But never mind. But so he was quite a keen photographer, right? And so he set up this system of wire-activated cameras, right? So what you do is you just stick a whole bunch of cameras with wires, and as you trip the wires, you'll take pictures, and you'll create a sequence of pictures, and that'll tell you something about what you're doing. Okay. So if you go and look at some of the paintings, and I had a quick look, right? People will always say, oh yes, that's always true for horses, right? But notice when it's true, right? See, they're always extended, flying. That's what most artists thought was the case. So this is the sequence of pictures that he collected. So it is true that you have unsupported transit, but it's true in this stage, not in that stage, right? Interestingly enough. So maybe even on this term, you can learn something interesting, right, from these sort of experiments. So of course, he was very, very famous for this, right? This is probably this and pictures of Yosemite, I think, made him a famous and weird man. I have a video here of this, which unfortunately doesn't play because this had to be a PDF, but trust me, it's a great video. And it's fascinating because it had some very interesting impact on artists at the time, right? So Degas loved this stuff, right, because he was very, very keen with motion of various kinds. But Rodin hated it, right? He has this idea, oh, it is the artist, right, who is truthful. and it is photography which flies, for in reality time does not stop, right? So it was an interesting cultural event, right? The fact that you do get to freeze time and you do get to understand how things happen which you cannot see with your eyes is a fascinating and fantastic development in science, right? And what we're trying to do here in some degrees, or people are trying to do, is to try and bring that down to the very shortest and fastest interactions that you can have in proteins and so on. So the first work that was done on this, on the Photosystem II, so that's this specific event here where you split water, right? That's what you want to do. So you have your little chlorophyll over here, which is sensitive to 680 nanometers, which does something, right? And what you want to do is you want to see this. Now, it turns out it has 4 or 5 actually intermediate stages. It's all very complicated. You really should, if you're interested in this, there are 2 Nature papers out on this from the past couple of years from various groups looking at this. And there's the cryo. So this is stuff that's frozen with very good resolution. So you can see the photosystem that was investigated in that way. But then also there's the pump probe event where they shine a laser light. So this is exactly the same as Muybridge effectively. What you do is you shine an optical laser light, and then a minute after you come in with the X-rays and you take a snapshot. And the X-rays are only 100 femtoseconds or 50 femtoseconds long, so it's frozen in time, right? And you do that with a specific delay, and this delay can be quite long, and you can snap through the various transitions, and you can see how the conformational changes happen. And you can do something, in this case, with something that wasn't cryo-cooled, right? So you can look at the difference between room temperature and cold systems. So it's the first example, if you like, of how you can actually go into the dynamic regime and see what happens with these systems, possibly in real time. Again, nanocrystalline, right? Another very interesting thing is people saying, oh, can we image live things, right? We keep looking at dead stuff that's been killed in various cases. Is it any different, right? Can we actually see the difference between life and death? Well, at the moment, not, right? But it's interesting to think about this a little bit. So this experiment was done now 4 or 5 years ago. The dose that we deposit onto these with an Xray FEL is about 100 million Gray, right? So just to put that in context, 20 Gray will kill you, which is unfortunate. So 50 to 60 Gray is typically the dose that you'll irradiate tumors if you go to a medical physics facility, right? Probably not even cockroaches survive 25,000 Gray, right? And so here you're looking at really, really ridiculous numbers off the scale, right? Of course, the thing blows up because it's immediately created. What you do is you immediately create a hot, dense plasma in sort of stellar interior conditions from a bacteria. So anyway, so this here is an image that shows you that they're actually alive because they're dyed, so you have some fluorescence, and you see that the membranes didn't pop when you inject them into the vacuum, and you can do diffraction of them. But unfortunately, and this still is the case today, the resolution for these things is just not good enough. There's not enough photons, right? So here are the limits around, I think it's quoted to be between 20 and 30 nanometers. Currently, the best people can do is about 10 nanometer resolution, which is not at the atomic level yet, and is actually very, very hard to do. But what you see here is diffraction patterns, and the reconstruction, and this is what Nomarski microscopy looks like for the same thing, right? So you get some image, you get some idea of what they're like. It's not quite good enough, right? So this is still work in progress, of course, but it's fascinating that you can already get so far. And of course, this has to be done for a single particle, right? You can't really integrate. Okay, very good. So that's the bit of imaging, right? Where what you're looking at is you're hoping that you're not depositing too much energy in your system, right? Now, the stuff that I'm slightly more interested in even is, well, what happens if you do deposit this stuff in, right? So you can look at the scattering component, but you can also look at the absorption component, right? So you could say, okay, well, but a lot of energy goes into these systems. What can I do with that? So this here is the idea, as I said before, of creating hot, dense plasmas in a tailored way, right? So the idea is fundamentally simple as an experiment. You just take the pulse and you focus it down. It's a very high brightness pulse. Now it becomes a high intensity pulse. And you can now do about 10 to the 19, 10 to the 20 watts per square centimeter at several keV, right? Those are extraordinary numbers that up until very, very recently were only really achievable for the biggest optical lasers. But you can now do this, and you can enter well into the nonlinear Xray regime. I won't talk about that, but you can do some very crazy things. But one of the nice things you can do is you can deposit a whole bunch of energy in a system, and you can create a nice plasma, and you can tailor the plasma conditions. So what can we do? Well, so this is a plot of temperature and density, just to give you a feel, right? 10 to the 23 electrons per centimeter squared is most of the stuff in this room, right, by and large. And a temperature, so this is in EV, right? So that's already 11,000 EV. So these here are the tracks that a pellet on the National Ignition Facility takes, right? So this is the fuel as you're trying to bring it to fusion burn on the biggest laser on Earth, right? So it starts down here, it's cold, and then it's driven up here, and then you have fusion happening somewhere up there. These are some experiments that have happened over the past on big optical laser systems where people try and generate hot dense plasmas, right? And this is some of the work that we've been doing on isochoric heating. So isochoric simply means you deposit all your energy and there's no change in volume within the time scheme of the experiment, right? So you start somewhere down here, and what you see is very interesting is, of course, these are different metals that we've used, but you can drive them into the conditions where they intersect with the temperature density diagram of stars, effectively, right? So this is our sun, these are white dwarfs, and a whole bunch of things in between. So this is not the core, of course, that you couldn't do, right? You just don't have enough energy. But you can get about halfway into the center of our sun. So you can dial and create with almost exquisite accuracy these sort of conditions as you wish and as you want, based on the science that you want to do. And that's very, very reliable. And there's a lot of indication that you can go a lot further. So what that allows you to do, I'll just give you one brief example, right? So you know this is the textbook picture of an atom, right? So you have atomic states and electrons in them, and then you have some continuum, and it's in every textbook for high school students that you ever had, which is great. You can do fancy quantum modeling of this stuff, and of course you'll get all your states and density functional theory, whatever else you want to use. It's not that important. But now you can go and you can measure this as well. So this here is an experimental outline for this charge state, and so you can map the electron density for a specific ion state. Now, this is just the ground state aluminium, not too interesting. Everybody knows what that is. But it turns out you can do this for the Taylor plasma as well. So you get to pick your temperature and density, and you can map out the electronic structure and the states and where they sit and so on with some quite nice precision, right? And so this is what this figure is here. So this is stuff that was now published several years ago. But you look and you can find the full map of the electronic structure. And that's interesting because this is not a cold system. This is now a system that's up to completely ionized, and it now tells you where your states sit. And it tells you what the equation of state is, and it also has some information on dynamical processes. So that's fascinating, right? Another thing that you can do, and I mainly put this in for the video, which now won't work, right? But there's a very nice dynamics idea where what you do is you do, again, another pump probe experiment, right? And here, you freeze time with the FEL, but you drive a shock wave through a system. So this is now here done in diamonds. So you create a highly compressed diamond sample, and a shock wave propagates. So that's one way to create high-density systems. Right? So that comes from up here. And then you focus your FEL, and you do this thing called phase contrast imaging, and you get an image down here. So this is work that was done by Andreas Schropp and Bob Nagler and others at LCLS. And what you can see is that you create a sequence of waves, and as those waves propagate through, you see different phases step through. So you can see this, and you can watch this in real time. So you have to trust me because the video doesn't work. But you can see as the wave and the shock wave propagates through, you can actually image the transformations that you get behind it. And you can do that in real time, exactly the way Muybridge effectively did, right? By snapshotting through the system. So that's what it looks like. That's where the wave should have come through, and then the shock would have propagated down here. The last thing I'm going to tell you, and then I'll wrap up, is one way in which you can go off and you can beat some of the limitations, even in the case of FELs, and you can actually tailor your systems to combine atomic and plasma physics to beat even the fundamental timescales that you have here, right? So what we're trying to do here, this is an experiment that we carried out now a couple of years ago, is we're looking at electron dynamics, right? I told you electron collisional dynamics is the main process that induces damage in various proteins when you excite systems. So it's a very interesting question to know how long it takes to induce damage. How long does it take, and how easy is it for electrons to collisionally ionize other electrons? Because that's the main mechanism. It's not so much the X-rays, it's the electrons flying around doing damage, right? So how on earth do you do this, given that an electron interaction timescale is on the attosecond range, right? There's no camera that's framed to that. There's almost no process that can do this. It's very hard to do, right? It's very, very quick. So how do you time this? Well, there's a very simple idea behind this, and it is you build yourself an Auger clock, right? So you know the typical recombination in light elements is governed by the Auger process, right? So the lifetime of a core hole in a system is going to be determined by a recombination mechanism of electrons, right? And so if you create a core hole here, that will eventually recombine, and it'll recombine quite quickly, right? The Auger lifetimes are between 1 to 10 femtoseconds, so they're quite short. But for those 1 to 3 femtoseconds, well, you're going to have an excited state. So the idea here is that we tailor a specific plasma state, and this is now no longer a condensed matter state. It's a state with a relatively high amount of inner core ionization. So we make a plasma, and it's hot. And then we tune the LCLS to a specific resonance transition. Now, the idea here is that if you had no collisions, right? What would happen is, well, in the absence of collisions, what you'd get is, some sort of Rabi flopping or something maybe, right? So you just drive electrons up, and then they recombine and up and down and so on. And what you'd find is that every now and then you'd get a K-alpha emission out. And so you'd get a specific line transition, which is this red here indicated here, right? Transmission between 1 and 2, which is what you're pumping. But imagine that you have collisions, right? So if you do have collisions, then what happens is you change your charge state. And the collisions are on the timescale of the Auger process. So what happens is you get up or down shifted photons. So all you now have to do is you have to count the up and down shifted photons, and that'll give you a timescale for the collisional processes timed back to an inner shell atomic process, right? All of this driven by an FEL. Okay, so this is the experimental data if you're interested in it, right? So that's the peak of the pulse, and these are the wings. These are all the collisional events that you can see. You can see 1, 2, 3 collisional events that happen within a single lifetime that's, in this case, I think it's around 3 femtoseconds, right? So the process is much, much, much faster. It's on the order, I think, of 300 to 400 attoseconds, right? And you can time this, and then that can help you construct different cross-sections and teach you something about collisional dynamics. Okay, so I think it's an exciting time for X-ray science, right? You really have a machine that allows you to do things that you couldn't do before, and it really is, it all comes down to peak spectral brightness. And you can now come up with some crazy schemes to do interesting things. I've talked to you a little bit about serial femtosecond crystallography, which is the stuff that people have found very, very successful. The big dream of single particle, single molecule imaging is still somewhat away. We still don't have enough juice. We need another 1 to 2 orders of magnitude more photons maybe, but it's something that people are working on, and maybe in the near future we'll get there. We can recreate stellar and planetary core conditions in the laboratory in these systems and study them with all the beautiful techniques that we know of from condensed matter physics. And that's quite powerful because it gives us access to a new type of diagnostic of some very extreme systems. And I think I'll leave it with that. Thank you for your attention.